Professor Mikhail Osipov from the University of Strathclyde. Thank you.
Okay, so that's the last talk, which will be short, so only 20 minutes, so I will only outline some of the points. So this is the work which has been done together with my collaborators from Russian Academy of Sciences and Technical University of Munich, and this is about the orientational ordering of anisotropic nanoparticles in diblock copolymers. And so this has a story, because a very popular way of producing new soft materials is to introduce various types of nanoparticles into nematic and smectic liquid crystals. And it has been, so that's done experimentally by many groups in the world, because there is strong evidence that in many cases this enables one to increase to improve the performance, say, of liquid crystal displays, to improve relaxation times, switching times, and even to extend the range of some phases, like, for example, the blue phase, which is important for lasing. But then the next step would be to think, is it possible to improve the properties of the block copolymer materials, doing the same trick by introducing the nanoparticles, and simultaneously to bring these block copolymers closer to liquid crystals, because what is the primary, my primary interest here is the induced orientational order of nanoparticles in block copolymers. So then, for example, one thing which has been very well documented is the change of the transition temperature in the simplest case, the nematic isotropic transition temperature in simple liquid crystals. And so sometimes there is just a decrease of the transition temperature, which can easily be explained as a dilution. So you simply dilute the material by nanoparticles. But in many cases also the increase of the transition temperature is observed up to 10 degrees. And if you look at the systems where this is observed, then obviously in this case the nanoparticles possess some kind of anisotropy. Either they are geometrically anisotropic, or they possess a strong polarization if they are ferroelectric nanoparticles, or strong magnetization. So something should be really anisotropic, and then this can possibly explain this stabilization of the nematic phase. And so we have done work on both types of materials, but as I say, I will only say something about this. Yes, so what's also important, so these are the computer simulations produced in the group by Claudio Zannoni, which are quite important to illustrate that if we want to model these systems seriously, then one has to take into account that nanoparticle is not simply a rod or a sphere, that it has a coating which stabilizes the whole liquid crystal phase, and it prevents separation and formation of clusters. And so, for example, in this case, in simulations, this coating is modeled by these anisotropic mesogenic groups which are linked to the central nanoparticle. And of course, this degree of sophistication is quite difficult to achieve in the simple molecular theory. So in the molecular theory, we still model nanoparticles as rigid bodies with some effective interaction energy. And so then the simplest way what one can do in the case of nematic liquid crystal is simply to generalize the popular Meyer-Zauper model for nematic liquid crystals. So that just to consider this as a two-component system, where nanoparticles are treated as kind of molecules. So this is a two-component mixture where the concentration of nanoparticles is small, so that they do not interact with each other, but they interact with the nematic with the molecules of the nematic host. And then, even in this case, a number of simple results can be obtained. For example, that's how the isotropic nematic transition temperature depends on nanoparticle concentration, depending on the anisotropy of the interaction between the nanoparticle and the liquid crystal molecule. And we understand that even though the concentration of nanoparticles in these systems, both in theory and experiment, is of the order of percent, a few percent, but the nanoparticle is, say, a metal object or a ferroelectric object, which is 2 or 3 times bigger in size than the molecule. And if it is anisotropic, then the strength of the anisotropic interaction may be quite large. And so as a result, for example, so one can see that there are 3 different possibilities. So either there is just dilution, so for spherical nanoparticles. For very anisotropic nanoparticles, you have this stabilization of the nematic phase, which is quite rare. And then in most cases, what is observed that the transition temperature is practically intact, which in fact indicates that there is a compensation, that the dilution is compensated by a relatively weak contribution from anisotropic interaction. And so that's again this case where we can consider how the nematic isotropic transition depends on the strength of this anisotropic interaction. And so we can see that, here we are. Yeah, so this is the key, this is the region of weak anisotropy. Again, here the dilution is compensated by anisotropic interaction, and it's possible to get a simple analytical expression for the approximate, of course, for the nematic isotropic transition temperature, which shows the effect of this anisotropic interaction. So this is basically, that's not the main focus of this talk, so I'm just trying to say that these so-called liquid crystal nanocomposites, they exist in various forms and shapes. And so now if we just switch to the block copolymers, then what are block copolymers? So block copolymers are composed of blocks, and these blocks are formed by flexible chains. So I'm talking for the moment about the simplest block copolymers, which are so-called coil-coil, so that the chains are flexible, sufficiently long, so they're approximately Gaussian, and as a result these systems form a variety of phases. So the most important ones are the lamellar phase and the hexagonal phase, which is composed of cylinders. And what is interesting about these block copolymers from the physical point of view is that this system is anisotropic. So say lamellar phase is geometrically anisotropic. But for example, dielectric anisotropy, optical anisotropy, is very, very small. And the reason is that it's only geometrical anisotropy. Within each block, the material is isotropic. So there is some very small contribution coming from the surface area. And this actually is quite important for these materials, because block copolymers are important technological materials. And so they're used in many areas. And people already started to add nanoparticles to block copolymers, but mostly spherical nanoparticles, because even spherical nanoparticles seem to improve their mechanical, electric, and other properties. So this is ongoing research. And so what was our idea here? Our idea was that if it is possible to embed sufficiently anisotropic nanoparticles, say, into the lamellar phase, and if they are somehow orientationally ordered inside this phase, then the, say, dielectric anisotropy and optical anisotropy of this system can be raised significantly, even if we add just a tiny fraction of these nanoparticles. And then why this is important for these materials? Because the great technological problem is how to align them. So there is no such easy way to align block copolymers as, for example, to align liquid crystals. And so people invent various things which are quite complicated and costly. While in this case it would be possible just to apply electric field and to align, say, the hexagonal face of a block copolymer quite nicely. At least this is a dream. So this was a motivation for this work. And so now if we look more closely at, so let us model our nanoparticle by Dumble for simplicity, and we assume that this sphere, say, likes the molecule, the monomers in block B, and it hates the monomers in block A. And so now imagine that this nanoparticle is somewhere in the middle of the block. There, of course, if it is sufficiently small, then it doesn't feel the boundary, so it can't be orientationally ordered. So there is no orientational order, and then it doesn't contribute to the anisotropy, not interesting for us. But if it is close to the surface, then you see, for example, its center is here, and then it is restricted because this ball doesn't want to go into the block A. And so as a result, it is forced to be more or less parallel to the surface. And if the same nanoparticle for some reason is located in the block A, then it tends to be perpendicular to the surface, because at least one of these spheres then has low energy. So we expect the orientational order of such dumbbells or nanoparticles in this boundary layer. How thick is this boundary layer, of course, depends on the parameters and mostly on the length of this nanoparticle compared to the size of the block. And so now then, again, we try to develop some simple statistical mechanical theory, starting from the simple interaction potential. Starting from simple interaction potential between this sphere and the monomers A and B, so assuming different constants to describe this discrimination. And so then, in the general case, the free energy of this system is the sum of several terms. So firstly, there is a conformational free energy of one individual chain. Then there is this well-known term in block copolymers which describes repulsion between different monomers, which is related to the so-called Flory-Higgins parameter, and which promotes the separation. So it promotes the separation of one block from another. Now, if we now consider the contribution from nanoparticles, there are two terms which describe interaction of the nanoparticle with monomers A and B. And finally, there is this orientational entropy, which is well known in the theory of liquid crystals, which comes into play if there is some degree of orientational order. And so now we can then use this free energy to minimize it, to get the expression for the one particle density of these nanoparticles. And then we just consider the matrix, which can be either lamella or hexagonal phase with this general expression for the order parameter. So this is well known. And the key result which we rely on is the expansion of the free energy in powers of this order parameter. But what is important is not the expansion, it's trivial, but the functions, the coefficients, have been expressed in terms of the parameters of the matrix of the block copolymer without nanoparticles by Leibler. So that's a seminal work where asymptotically exact formulas have been obtained at least for the quadratic coefficient, which are exact in the case of long chains. And so we just start from that, and so then we expand the remaining part of the free energy, which is the contribution from nanoparticles, again in terms of these order parameters. And so in this way, one obtains the corrections to these coefficients in the Landau expansion, which depend on the parameters of the nanoparticles and the parameters of the interaction potential between nanoparticles and the and the monomers. And then in this way one can obtain the phase diagrams where one can see what happens, for example, if one increases the concentration of nanoparticles, then basically hexagonal phase is induced, or what happens if we increase and change sign of the discrimination energy. So again, there are in some cases, so these asymmetric cases is when the block copolymer is asymmetric, when the length of one block is different from the length of another. Here the most interesting phase diagrams occur. So if you move in this way, for example, one expects multiple phase transitions induced by nanoparticles. So and then of course and so that possible to get the density profiles and order parameter profiles, and indeed this confirms the general idea that order parameter is negative in one block close to the surface, and then it is positive in another block close to the surface. And because the density of these, concentration of these nanoparticles is different on both sides of the boundary, then there is a net orientational effect, which is not very strong because most of the nanoparticles sit inside the block. And so let's keep this. And then, my collaborators from Russian Academy of Sciences and University of Munich, they also made dissipative particle dynamic simulations of these systems to see if this is something similar to the theory. And so in this case, the block copolymer was modeled by the chain composed of 20 spheres. So then depending on how many spheres are in each block. And then the nanoparticle was a rigid object composed of 3 to 7 spheres. And so then there is a standard dissipative particle dynamic simulation with a reasonable system size have been undertaken. And for example, that's just the snapshots which illustrate how the nanoparticles can induce a transition from the hexagonal phase to the lamellar phase, just by changing the volume fraction of nanoparticles. So you need a significant volume fraction in this type of simulations of about 10% to induce that. And then, of course, all other things can be considered. For example, what's the effect of the nanoparticle length? And here we observe the phase separation. So if the nanoparticle length is 7 spheres in this case, so 3 spheres is fine, 5 is also okay, but in 7 spheres you can see that there is clearly there is a phase separation in this system. And then, so again, some curves for the nematic order parameter have been extracted from simulation, and they are not quantitatively, they can't be compared with the theory, but qualitatively they look similar. So you see that indeed it's slightly negative on one side of the boundary, and then it is much bigger and positive on another side of the boundary. And again, there are also curves for the nanoparticle concentration. So there is indeed a net orientational order in this system. And this is quite interesting from my point of view, because that's a completely different system from ordinary liquid crystals. Here, anisotropic objects are orientationally ordered not because they interact between each other, but because they are coupled to the structure. So that's essentially a broad surface effect. And then finally, that's the phase diagram which has been extracted from simulations. And so here is that's the composition of the original block, copolymer, so a fraction of the lengths in 2 blocks. And this is the volume fraction of nanoparticles. And so in principle, in this system, one can observe not only hexagonal phase and the lamellar phase, but also other phases like perforated, lamellar, bicontinuous, and things like that, which are not yet described theoretically. And so thank you for your attention.
I think we have time for one quick question.
A question, yeah. To generate your, like, for example, the lamellar or the hexagonal phase composition profiles for just the copolymers, have you tried comparing to, like, polymer self-consistent field theory to see if that's a more computationally accessible route to computing these things?
Yes, the thing is that self-consistent field theory is so computationally expensive, so that in some cases they can produce few points.
Yes,
in the profiles, no more than that.
Yeah.
And also they do not look at the dependence on the temperature or things like that.
Okay.
Yeah, so for pure block copolymers, they have pretty good results.
Sure.
But we're not doing this because we just rely on linear theory for.
Okay.
Yeah, but in the case of composites, that's very little what has been done.
Okay.
So they mostly consider pure polymers.
Yeah.
But that's a separate question, but we do not have time
Yeah, no, I was
to
just curious
discuss
about
it
that.
now.
Okay, thanks.
Okay, well, let's thank Professor Osipov again, and that's the end of our session.